Hey guys, a very good day to you all. In this video, we will understand the integrated rate law for zero order reaction. And along with this, we will also understand the units of rate constant for zero order reaction and half-life of zero order reaction. So let's start with this video. And to understand the integrated rate law, let us consider a simple reaction over here. Now here, as you can see, A is nothing but the reactant and it gives us products, and this one is nothing but the stoichiometric coefficient. And we all know the formula for rate of the reaction is nothing but 1 upon the stoichiometric coefficient into change in concentration of A divided by change in time. And according to the differential rate law, we get another formula for rate of the reaction, that is nothing but K into molar concentration of A raised to 0. Now here this K is nothing but the rate constant, and we have considered molar concentration of A because A is our reactant, and it is raised to the power 0 because we are considering zero order reactions. Now, if you all do not know how do we get these two formulas of rate, then you can watch my previous videos. The link of the playlist is given in the description box below, or you can simply click on this I button which is present on the right top corner of your screen. Now guys, if you observe this equation number 1 and if you observe this equation number 2, what you notice is that the left hand side of both of them is same, and since the left hand sides are same, then obviously the right hand sides will also be same. So from equation number 1 and 2, what we get is somewhat this equation. We have just equalized the right hand sides. Am I right? If the left hand sides are same, then obviously the right hand side will also be same. Now what I'm going to do is that I am going to multiply this equation by -1. So when I multiply by this equation by -1, this is something that we get. Now next, what we are going to do is that we are going to shift this dt to the right hand side. So shifting this dt to the right hand side, what we get is this equation, and we name this equation to be equation number 3. Now let us keep this equation aside for next 2 to 3 minutes. Now if you look at our equation carefully, let at time is equals to 0, which means that when the reaction has not started yet, we assume that the molar concentration of reactants is A0. So your reaction has not yet started, and we assume the initial molar concentration of A as A0. We have assumed this value, okay? And obviously if your reaction has not yet started, then the concentration of products will obviously be 0. Now what we do is that we start the reaction, and after certain time t1, okay, so after time t1, we assume that the molar concentration of reactant A is AT. So after certain time, we assume that now the molar concentration has changed from A0 to AT. Now my one simple question to y'all, between this A0 and AT, which will be greater? Obviously molar concentration A0 will be greater. Why? Because after certain time t1, some amount of reactants get converted into products. Therefore, the amount of reactants decreases, and if the amount of reactants decreases, then obviously guys, the concentration of reactants will also decrease. Therefore, AT will always be less than A0. Okay, now let us consider our equation number 3 again. Now in this equation, what we are going to do next is that we are going to apply definite integrals to this equation. Definite integrals. Now if you observe on the left hand side, can I write as 1 into change in concentration of A? I can multiply 1 wherever I want. Okay. Now applying definite integrals, so you need to be careful over here. So when now before applying definite integrals, on right hand side, if you observe, you are applying definite integrals with respect to dt. T is nothing but time. So your limits should also be according to the time. And if you observe on the left hand side, when you are applying definite integrals, you are applying it with respect to dA, and A is nothing but your molar concentration. So the limits should also be in terms of molar concentration. So when time was 0, so when time was 0, your molar concentration that you have assumed is A naught, and when time is T1, the molar concentration that we have assumed is AT. So I hope this part you have understood. If you have understood this part, then the rest is easy. Now if you observe, this minus k is nothing but a constant. So just let us remove this minus k out of this integration sign. Now guys, can I write the equation as something like this? And your limits are going to stay as it is. Now, what is the integration of 1 over here? So here the integration of 1 is nothing but concentration of A. I hope you all know integration. Integration of x. What is integration of x? Sorry, my bad guys. Integration of 1. Integration of 1 with respect to dx is nothing but x. So here we are having dA. So therefore, on the left hand side you will have molar concentration of A, and on the right hand side if you observe, there is time. So integration of 1 with respect to dt is nothing but t itself. Okay, and you don't forget to write the limits. Now just substitute the limits. So instead of molar concentration of A, just write AT over here, AT minus A naught, and instead of T we will just write T1 minus 0, upper limit minus lower limit, as simple as that. And finally we'll end up with somewhat this equation. Now again, let us multiply this whole equation by minus 1. So when you multiply this whole equation by minus 1, this is what we get. And let us now shift this T1 to the right hand side. So shifting this T1 to the right hand side, this is the final equation that we get. And this is called as your integrated rate law for the zero order reactions. Now, I hope you have understood the integrated rate law. Now let us move on. Now, don't forget, this K is nothing but a rate constant, and this T1 is nothing but the time T1, after time T1 that you have assumed. You can put time T1 as your convenience, as per your convenience. Okay. Now, let us find out the units of rate constant K. So, to find out the units, we are going to consider the same formula. But before that, these units of rate constant that we are going to find are for the zero order reactions. In the previous video, we have seen that the units of rate constant K for first order reactions. We have already found out the units of rate constant K for the first order reactions. In this video, we are going to find out the units of rate constant K for zero order reactions. So let us consider our main formula as it is. Okay. Now here, whenever you find out the units, you obviously refer to the formula. Now in the numerator, if you observe guys, in the numerator there is concentration, molar concentration minus molar concentration. Am I right? A naught is obviously in terms of molar concentration and AT is obviously in terms of molar concentration. So basically in the numerator, the unit that you can observe is molar concentration. And so in terms of molar concentration, the calculation is done in terms of molar concentration. So the units of molar concentration is nothing but moles per liter. Am I right? Molarity, moles per liter. And in the denominator, if you observe, there is nothing but time. And time can be in seconds, minutes, hours. According to your convenience, you can assume the time to be in seconds or minutes or even hours. So we just write it to be T. Now guys, can I write these units as somewhat like this? See, this liter will go into the denominator. Okay. Now, moving on. Now, further on, these are the units of rate constant, and you can even write it as mole into liter inverse into time inverse. So when you bring this denominator terms into the numerator, we have to add a negative sign into the powers. So this is as simple as that. The units of rate constant are very simple. I hope you have understood this as well. Now guys, let us understand what is half-life of zero order reactions. Now first of all, what is the meaning of half-life? Half-life is nothing but the time required for the concentration of reactants to become half. I repeat myself again. Half-life is the time required for the concentration of reactants to become half. So here is the definition of half-life. The time required for the reactant concentration, that is nothing but a concentration of reactants, to become half of that of initial concentration. So suppose if your initial concentration A naught is 1 molar, then the time required for the concentration to become 0.5 molar is called as half-life. Suppose if your initial concentration A naught is 0.6 molar, the time required for the concentration to become 0.3 molar is called as the half-life. Now to calculate half-life, we are going to consider same formula. Now guys, we need to make some modifications in this formula. See, at half-life, what is going to happen? The concentration of reactants is going to become half of that of initial concentration. If you guys, can I write that the concentration of reactants has now become half of that of initial concentration. Now just substituting this formula of AT as A naught upon 2 in this equation, then we get something like this. And after further on simplifications, we get the final formula for half-life, that is nothing but K is equals to initial concentration divided by 2 times T1. Now here the value of T1 that you will get will obviously be nothing but the half-life. So for any zero order reaction, you are going to use this formula, and with the help of this formula, you are going to calculate the value of T1, and the value of T1 that you will get, that is nothing but the half-life of that particular zero order reaction. So guys, I hope this video is clear for you, and if you like this video, then please don't forget to subscribe to our channel and go check out my channel where I uploaded physics and chemistry videos. They might be helpful for you. And guys, thank you for watching this video.